Welcome to 10.7. In this section we're going to discuss complex numbers. Complex numbers are related to radicals. Complex numbers are often called imaginary numbers, and there's a technical difference between the two words. Now, just because it's called imaginary does not mean that it doesn't really exist. Okay, so these are useful in a lot of applied areas. Okay, an imaginary number, let's start with the basic definition of this, which is I. The imaginary unit, which is written, it's usually written with a cursive I, lowercase, is the number whose square is -1. Okay, so we just say the number whose square is -1 is I. In other words, if its square is -1, well, if you take the square root of both sides of this equation, you would get I is equal to the square root of -1. So I is equal to the square root of -1. And that's what you should, well, memorize right there. Both of these really, but I is the square root of -1. Now, as you know, there's no number whose square is equal to -1. Okay, so it's not a real number. It can't be used for counting. However, these are actually used a lot in applied problems where you'll start out with a real applied problem and the answer will be a real answer. But in order to get from the problem to the answer, you have to go through imaginary numbers sometimes to get to the final answer. And that's where these are really useful. Now, we're not going to get into any real advanced applications here, but that's where they are used. Okay, we're going to just practice the basics of I and using I right here. Let's rewrite all of these radicals. Notice they all have negatives under the radicals, so there's no real solution to any of these. These are not real numbers, but they can be written in terms of I. Okay, so for example, the square root of -25. We could think of that as the square root of 25 times -1. Actually, I'm going to reverse the order of that. Let's write it as the square root of -1 times 25. And you could think of that as two radicals, the square root of -1 times the square root of 25, which would be I times 5. Now typically you would write it 5I just because letters tend to come after numbers in the way standard order that things are written. Okay, so the square root of -25 could be written as 5I. Those are equivalent. The square root of -3 could be thought of as the square root of -1 times the square root of 3, or now the square root of 3 does not simplify, but the square root of -1 does, so you would have I times the square root of 3. Now this is actually an exception where it's really best to put the I out front, because if you write it like this, the square root of 3 times I, it's really sometimes hard to tell if that I is supposed to be under the radical or not. So if you have radicals, I tend to put whatever's not under the radical out front, even if it's a letter and what's under the radical is a number. Okay, so basically what you might be noticing here is that this negative that's under the radical essentially turns into that I. That negative right there turns into that I, and then everything else just stays. Square root of 25 becomes 5, square root of 3 stays square root of 3. Okay? And the next one, we have the negative of the square root of -50. Okay, this negative has nothing to do with this negative. Those are completely separate. So this negative out front, it's just going to hang out front while we figure out how to rewrite this radical -50 in terms of I. So that negative just hangs out front. That's the first negative. Now radical -50 can be thought of as the square root of -1 times the square root of 50. Square root of -1 is I, so we have -I times radical 50. And of course you want to go see if that simplifies. Radical 50 I can divide by 2 to get 25, and I can divide that by 5 to get 5. So that does simplify into 5 radical 2. So you could write this as -5I times radical 2, where that 5 here came out front and that 2 stayed under that radical. Okay, and this next example we have the square root of -2 times the square root of -7. Well, let's rewrite each individual radical first in terms of I, then we'll multiply them together. So radical -2, as you know, that negative basically turns into an I, so you have I times radical 2 times radical -7 would be I times radical 7. Okay, let's keep simplifying though here because we have an I times an I. Well, I times I is I squared. And we also have radical 2 times radical 7. We could combine those into one radical and call it radical 14 since neither of those simplifies. And from here we can keep simplifying a little more. I squared is defined up here to be -1 because I is the number whose square root is -1. So I squared is -1. So this actually becomes the negative of the square root of 14. So this one is interesting. You actually do get a real number solution when you simplify. This is a real number, although neither of these two here are real numbers. So that's sort of an example of how you can go through imaginary numbers and actually end up with a real answer. Okay, on the next example, it's very similar to this one we just did. We have the square root of -25, which we did up here, found that that is 5i, times the square root of -1. Well, the square root of -1 is defined as I. So this one gives us 5i squared, and I squared is equal to -1, so this part becomes -1. So you have 5 times -1, or just -5. Again, another example of going from imaginary numbers and then they simplify and turn into a real number. Okay, here's another example. Square root of 27. Well, there's no negatives here, nothing to deal with, but we can simplify that. 27 divided by 3 is 9, divided by 3 is 3. So we can rewrite 27 as 3 radical 3. And then radical -3 we found up here is equivalent to I times radical 3. So simplifying and just reordering a little bit, we can combine this radical 3 times that radical 3. So these two, radical 3 times radical 3 is 3. So that gives us 3 times I times 3. Simplifying further, that gives us 9i. And in this next example, radical -8 over radical 2. Radical -8 can be written as I times radical 8. Radical 2 does not simplify as is. Now there's a couple ways you could go about doing this. You could rationalize the denominator, or what I'm going to do is first simplify radical 8, because 8 is divisible by 2, 2 and 2. So I'm going to rewrite radical 8 as 2 radical 2. Now it's over radical 2, and everything is factored here, so we can cancel those radical 2's to just get simply 2i. Okay, those are dealing with imaginary numbers. So I is the imaginary number. Because I has this special role as meaning imaginary number, it's a bad choice to use as a variable name. Okay, I typically avoid using I for anything else because I means the square root of -1. The difference between an imaginary number and a complex number is simply that a complex number is actually the sum of a real number and an imaginary number. So a complex number can be written in the form a plus bi, where a and b are both real numbers. So for example, let's add a little example in here. You could have 2 plus 3i. That's considered a complex number because it has a real part, which is 2, and an imaginary part, which is 3i. And that's exactly how these two things are defined as. That a is referred to as the real part, because it is just simply a real number, and the bi is referred to as the imaginary part of the complex number. Now, here's just a special note. All real numbers technically are also complex numbers because they can be written a plus 0i. So the number, for example, 2 could be written 2 plus 0i. So because it can be written in this form, it is in fact a complex number, although it does not have an imaginary part. So all real numbers are complex numbers. A pure imaginary number is when the first part, the real part, is 0, so a is 0, but b does not equal 0. So for example, if it just said 2i, that's just a pure imaginary number because there's no real part to it. It's not being added to a real number. Okay, this is a chart from your book that kind of explains all the different types of numbers and how they're related. You don't necessarily need to memorize this or anything, but it does kind of hopefully help you to understand all this terminology. We have complex numbers as sort of the umbrella here. They're of the form a plus bi. Here's some examples of those like we were just discussing. Now complex numbers breaks down into two parts: real numbers and complex numbers that are not real, which would basically just be called imaginary numbers, but complex numbers that are not real. So real numbers have no i's in them because I is the imaginary part. Real numbers are what you're used to dealing with. They can be positive, negative, whole numbers, fractions, decimals, whatever. Real numbers, we break them down into two types: rational, which can be written as fractions or repeating decimals, and irrational, which have no repeating decimals and cannot be written as fractions. And we've discussed those a little bit. Now other complex numbers can be broken down into two types: imaginary and then just all others. So imaginary numbers are ones that just have i's, and then all other complex numbers would be things of this sort: 3 plus 5i, 6 minus 0.2i. They have both a real part and an imaginary part because neither a equals 0 nor b equals 0. Okay, let's practice working with complex numbers. That's the more important part here, is can we work with them? So let's practice adding and subtracting complex numbers first, then we'll multiply and divide. So adding complex numbers. This is one complex number because it's in the form a plus bi, 5 plus 2i. This is a second complex number, 4 minus 3i. Here the b is actually negative 3. The b would include that negative there. So when you add complex numbers, really these parentheses are not necessary, so I'm going to rewrite it without those parentheses to get 5 plus 2i plus 4 minus 3i. And then you do math just the way you would normally do it. Combine like terms, so we can combine the 5 plus 4 to give us 9. And we add the I terms just like you would if it was 2x minus 3x. So 2i minus 3i would give us, you would subtract their coefficients. So 2 minus 3 is negative 1. So you would have negative 1i. So this one would simplify to 9 minus I. Okay, this next example says 6x minus 2 minus I. And I had fully intended to put 6i minus 2i, minus 2 minus I. Change that x there to an I. That's just habit from typing x too many times. So that should say 6i minus 2 minus I. This isn't a complex number, 6i is, because it's missing the real part, but it's still a complex number because it has an I. And 2 minus I is another complex number, and we're subtracting them. So just like you would normally, we do have to distribute that negative out over those parentheses to give us 6i minus 2 plus I. Now combining like terms, we can combine the 6i plus I to give us 7i, and then we have a minus 2. Now that's correct, however, you almost always with complex numbers write the real part first. It's just the standard way it's always done. So the real part is the negative 2, and the imaginary part is positive 7i. So I would actually write it in this order. Although this is not wrong, it's just not in standard order. Okay, subtracting these two complex numbers, we would have to multiply this negative 3 to give us positive 3. And these parentheses here are really not necessary. They're not doing anything. So I'm going to eliminate those. Negative 2 minus 4i, and then minus negative 3 is plus 3. Then we combine like terms. 3 minus 2 gives us 1. Then we have the minus 4i. Okay, so that's how you add and subtract complex numbers. Now let's look at multiplying two complex numbers. Okay, in this first example we have negative 5i times 3i. You're doing math the exact same you would if it was x's. The only difference is, well, you'll see when we do this one. We can multiply the negative 5 times the 3 to give us negative 15. And I times I gives us I squared. So this is the only difference. I squared is equal to negative 1. So in this case we have negative 15 times negative 1, which then simplifies to positive 15. Okay, just like you would regularly, we would have to distribute this next one out over the parentheses to give us, for the first term, negative 12i, and for the second term would be positive, 2 times 2 is 4, and then I squared. Now that I squared is equivalent to negative 1, so we have negative 12i plus 4 times negative 1, or negative 4, if I put it in standard order, it would be negative 4 minus 12i. And this next one has a binomial times a binomial, so we do have to FOIL. So in FOILing, our first term is 3 times 6, or 18. Our outside term is 3 times positive I to give us plus 3i. Our inside terms multiply together to give us negative 24i. And our last two terms are negative 4i times I, so negative 4i squared. Let's see, we have two like terms here that we can combine. 3i minus 24i. 3 minus 24 is negative 21i. Then we have minus 4i squared. I'm going to change that I squared to negative 1. So now we have another two like terms. 18, and this will combine to be positive 4. So 18 plus 4 is 22. So we end up with 22 minus 21i in this example. And in this next example down here, we have I minus 2i all squared. Don't forget, we would have to square the whole thing. Just write it out twice if it helps you. I minus 2i, oops, no, 1 minus 2i times 1 minus 2i. And then hopefully that helps you remember to FOIL. So the first two terms give us 1. The outside terms are 1 times negative 2i. Inside terms, 1 times negative 2i. And the last two terms are negative 2i times negative 2i. So that would be positive. The 2 times 2 gives us 4. And the I times I is I squared. Combining these two middle terms, we have negative 2i minus 2i. Those are like terms that will add to minus 4i. And then rewriting the I squared as negative 1. We have 1 minus 4 here, which is negative 3, minus 4i. And one last example here. This one's a special example. When we FOIL this one, the 6 times 6 becomes 36. The outside terms are 6 times minus 5i, so minus 30i. The inside terms are positive 5i times 6, so positive 30i. And the last two terms are 5i times negative 5i, so negative 25i squared. Now this one is special because if you'll notice, the inside and outside terms cancel. So if you have the same quantity and the only difference between these two complex numbers is a positive and a negative on the B, this will always happen. The middle terms will cancel. And then when we rewrite the I squared as negative 1, we have 36 minus 25 times negative 1. And if you'll notice, this is a real number. We've eliminated all i's. So 25 times negative 1 is positive 25, so this is 36 plus 25. See, 6 and 5 is 11, so plus, so that would be 61 in this example here. Okay, so that's how you add, subtract, and multiply complex numbers. Okay, here's a little new terminology for you. Conjugates, and this is similar to the one that we were just working. That's basically what this is referring to. The complex numbers a plus bi and a minus bi, they're called complex conjugates of each other. Conjugates, we've used that word before. That's where the sign changes. Okay, now in general, let's do a more general example like this last one. If you multiply together a plus bi times a minus bi, let's FOIL again. You'll have a squared. Outside terms are minus abi. Inside terms are plus abi. And the last two terms are minus b squared, I squared. So those middle terms will always cancel. And that I squared is negative 1. So you have a squared minus b squared times negative 1. Or more simply, a squared plus b squared. So a sum of two squares could be factored into two imaginary numbers if you wanted to. But typically we only factor a difference of two squares. Remember, this is a good point just to review. Remember, the a squared minus b squared factors into two real binomials, a plus b and a minus b. This is a squared plus b squared instead of a squared minus b squared. And it could factor into a product of two imaginary or complex binomials, a plus bi times a minus bi. And that's the real difference. However, it's rare that you would actually want to factor a real number into imaginary numbers because that would make it more complicated. Okay, let's compare these products. Now we can do these basically using a shortcut here because we have x plus 5 times x minus 5. Okay, I'm going to write it all out though because I don't want to lose any one. So the first two terms are x squared when we FOIL. The outside terms, we have x times negative 5 and the inside terms are x times positive 5. Those cancel, and then the last two terms are negative 25. To give us x squared minus 25. And this is an example of going backwards here and factoring that a squared minus b squared. Okay, let's look at x plus radical 5 times x minus radical 5. This one's a little different. Now the outside and inside terms will still cancel. Okay, the first term is x squared, but the outside term is minus radical 5x. The inside term is plus radical 5x, so I'm not even going to write it. The last term is minus radical 5 times radical 5. And radical 5 times radical 5 is 5. So that one multiplies into x squared minus 5. So if you look at this backwards, you could see how really this could be factored into two real numbers, a product of two binomials, where you treat 5 as being the square root of 5 squared, and that's how you use this a squared minus b squared to factor it. Now let's compare that to this, which this is an example of this. Okay, x is equivalent to a, b is equivalent to 5 in this example. So using this, we already know it should multiply out to be a squared, which would be x squared, plus the b squared. Now b is that coefficient of I, in this case is 5, so plus b squared would be 25. Now if you're not sure about how to do that, just FOIL it out, okay, to check. So if I was to FOIL this and do it the other way, I would get x squared minus 5xi plus 5xi. The last two terms would be minus 25i squared. That's an I squared. Those cancel. I squared is written as negative 1, and that does in fact give us x squared plus 25 squared. 25. Okay, so complex conjugates. The main takeaway here is that a plus bi and a minus bi are called complex conjugates of each other. Let's look at dividing complex numbers now. This is a little bit more complex. Dividing complex numbers, you use the same process as you would to basically to rationalize denominators. The trick is multiply by the conjugate, the complex conjugate of that denominator, because you have to get the i's out of the denominator. In order to make this expression look like this, write it in the form a plus bi, there's no fractions, so we've got to eliminate all the i's from the denominator. Now nothing here cancels because nothing is factored. We have a plus in the numerator and a minus in the denominator. So nothing can cancel. But what we can do is multiply by a fancy form of 1, which is what I'm going to do. So this would be 3 plus I over 2 minus 3i. The conjugate of the numerator would be to change that sign to become 2 plus 3i over itself. Now the reason why you would do that is because you already know from this, if you multiply a complex number times its conjugate, it turns into a real number. The i's go away, and that's what we want to do. Don't forget to FOIL all this, add parentheses if you need to. So in the numerator, FOILing, we have 3 times 2, or 6. The outside terms are 3 times positive 3i, so plus 9i. Inside terms give us plus 2i, and the last two terms give us plus 3i squared. In the denominator, we have this product of two conjugates. So the outside and inside terms cancel. The first two terms give us 4. Outside and inside cancels. And the last two terms are minus 3i times positive 3i, so minus 9i squared. Or you could just use this and jump straight to 4 plus 9. And then we keep simplifying, and eventually we will be able to write it in the form a plus bi. Let's see, in the numerator we have 6 plus 9i plus 2i is 11i. 3i squared is plus 3 times negative 1. In the denominator, that I squared becomes negative 1, so negative 1 times negative 9 is going to be positive 9, or you could have jumped to that to get 4 plus 9. And we're still not in the form a plus bi, so we've got to keep going. Let's see, in the numerator we can combine this 6 and this negative 3. 6 minus 3 is equal to 3. So that gives us 3 plus 11i. In the denominator, 4 plus 9 is 13. Now it's getting closer, but it's still not in this form that we want it in, a plus bi. We want it to look just like that, where a and b are real numbers. So all we have to do to write it like that is to split this into two fractions, 3/13 plus 11/13 times I. Now it's in the form a plus bi. So that's it. Okay, so if you're dividing complex numbers and you have i's in the denominator, and it's of the form a plus bi over a plus bi, you multiply by the fancy form of 1 in the form of the conjugate of that denominator over itself. So let's do that again for this example. 6 over 5i. We want to write it in the form a plus bi. Now, what I'm going to multiply this by is some sort of fancy form of 1. Now this does not have a sum or difference of two terms in the denominator, so it's even a little bit easier. I could multiply by 5i if I wanted to, but there's no reason to. All we really need to do is to make that I go away. And to make an I go away, you just have to multiply it by another I so that it turns into a negative 1. So on this one, I would just multiply by I over I. Keep it simple. In the numerator, then we have 6i, and in the denominator we have 5i squared. And I squared is equal to negative 1, so that would be negative 5. To write it in the form a plus bi, if you'll notice, there is no a. There is no real part. 6 over negative 5 is the b. That is the coefficient of the I. So it's just 0 plus negative 6/5 I, which is in this form, a plus bi. Okay, next let's look at powers of I. This is really interesting and kind of fun. There's some patterns that go on here. Okay, so let's just start by looking at I. I is equal to I. I squared is equal to negative 1. You know those two. Now I cubed. We could break that down into I squared times I. If I do that, I squared is equivalent to negative 1, and I is just I, so that would give us negative I. Now I to the fourth, to figure out how to simplify that, I could break that down into I squared times I squared, because I know both of those. I know I squared is equivalent to negative 1, so that's equivalent to negative 1 times negative 1, and that we know to equal positive 1. So far I is equal to I squared is equal to negative 1, I cubed happens to equal negative I, and I to the fourth is actually a real number, it's equivalent to 1. Let's keep going and see what happens. I to the fifth, we want to break that down into ones that we know, so how about I to the fourth times I to the first, and I'm breaking it down that way because I to the fourth is easy, it's just 1. So that gives us 1 times I, or simply I. I to the sixth, I'm going to try to break all these down into I to the fourth times something because I to the fourth is simply 1. So I'm going to break I to the sixth down into I to the fourth times I squared. I to the fourth is 1, and I squared is negative 1. So 1 times negative 1 gives us negative 1. I to the seventh, I could break down into I to the fourth times I cubed. I to the fourth is 1, and I cubed we figured out over here is negative I. So this one simply gives us negative I. I to the eighth, I could break down into I to the fourth times I to the fourth, which is 1 times 1, which is 1. Now look at what we just did. Do you see a pattern here? I and I. Negative 1, negative 1. Negative I, 1, 1. So when we break down I to the ninth, I'm going to break that down into I to the eighth times I to the first. I to the eighth is 1. So as you can see, all of these down here are going to be 1. So we're left with 1 times I, and this one also is I. Basically every fourth power is I. I to the first, I to the fifth, I to the ninth. If we added another 4 onto this number, notice the exponent is just increasing by 4 every time. We would have I to the 13th. It would also be I. Add 4 more onto 13, you get 17. So I to the 17th would also be I. And so on from there. I to the 10th is going to follow the same pattern because it breaks down into I to the 8th times I squared. And it's always going to break down into this times this. So it would be 1 times negative 1, or just negative 1. So if you'll look at these exponents, they're 2, 6, 10. They're increasing by 4 every time. So I to the next one would be 14th, would also be negative 1. I to the 18th would be negative 1. I to the 22nd. Okay, I to the 11th. Think you get the pattern here? It's also going to be negative I. And I to the 12th will follow that pattern. It'll also be 1. So once you know this pattern, if you can figure out where I to a power falls in this pattern, you can figure out what it is without having to actually multiply I by itself 11 times. Okay, I'm going to break this down just to show you how you would work it if you couldn't quite see where it's going to fall in the pattern in your head. You would want to break down 11 into 4 times something because I to the fourth is 1 and powers of I to the fourth are 1. So you would say, what's the biggest number that I can divide, or that goes into a number less than 11 that's divisible by 4? The largest number less than 11 that is divisible by 4, that would be 8. 8 is less than 11 but divisible by 4. So I could break that down into I to the 8th times I cubed. I chose 8 because it is a multiple of 4. So I to the 8th is 1, and I cubed, you have to remember, is negative I. So this would be negative I. I to the 40th, now we want to break that down into a power of 4, or a number that is divisible by 4. Well, 40 is divisible by 4. You could think of this as I to the 4th all to the 10th power. I to the 4th is 1, so you simply get 1. And that is because it would fall in line if you were to write out I to the 13th, 14th, 15th, 16th, 17, 18, 19, 20. 40 would fall in this last row down here. I to the 50. 50 is not divisible by 4, but we could break it down into, let's see, the biggest number that's less than 50 that is divisible by 4. You might have to play with your calculator a little to figure it out. That's fine. It's going to be 48. 48 is divisible by 4. So I could break this into 48 and 2. So I to the 48th we know is 1, and I squared we know is negative 1. So we get negative 1. Okay, and one last example here. This one is a little different. I to the negative 10. Okay, the pattern may or may not continue on in the negative direction here. I don't know. We haven't experimented with that. So instead, I would probably first just rewrite this without a negative exponent, because that we are sure of. We know we could write this as 1 over I to the positive 10 to get rid of the negative exponent. And then this I to the 10th we could rewrite or simplify. Well, see, I to the 10th we actually know from up here is equal to negative 1. So this would be 1 over negative 1. Simplifying just gives us negative 1. And that's it for complex numbers. We're going to use complex numbers throughout the next chapter. So that's it for chapter 10. Join in next for chapter 11.